All right, welcome to video 3 of Trig. There's a lot. Trig is a very, very big topic, as I mentioned in the first video. It's something that needs your patience. And trying to do it here in this fashion is not the best, but at least walking into your next class, whether it's Integrated 3, Honors Pre-Cal, you won't be at a loss. Hopefully you're watching these videos. Those of you that aren't, you're going to be at a loss come next year. We're going to have to do a lot of fixing of these types of things, and things are going to move much faster than you're ready for. And so that's something to think about. So hopefully you're watching these videos and doing the work. What I've got is I've got two triangles here, triangle day and triangle box. These triangles are similar. If you don't know about similarity, you should have watched those other videos. If you recall from those other videos, what it means to be similar is the same shape, but not the same size. Notice these are definitely not the same size. Triangle day has measurements 6, 8, 10. Triangle box has measurements 21, 28, 35. So they're definitely not congruent. But they are similar, and recall how we write similar. We would write triangle day, and then the similar symbol, which is just the tilde from Spanish, and then we have triangle box. All right, that's what it means to be, that's how we write that the triangles are similar. What it means is the sides have the same ratio as long as we get matching sides. So matching sides like side DA and side BO. They are matching sides, and if we look at their ratio is 6/21. I can write that like this. Now, to show you that these are definitely similar, if we pick two other matching sides, they need to be in the exact same ratio. So if I pick, say, side AY, which is 8, that would have to hold the same, that would have to be in a ratio with 28, and that ratio should be exactly the same as our first ratio, which it is. If I set up this fraction, 8/28, if we were to reduce these, 6/21 reduces by dividing by 3, and that reduces down to 2/7. And 8/28, if we divide them by 4, OMG, we also get 2/7, right? So that shows that these are similar. I don't actually need to do that, though. We have a theorem that we looked at before. I'm going to put that back up here again. We have this thing called AA similarity. What that means is if you have two angles of one triangle, this only works for triangles, if you have two angles for one triangle and they are exactly the same as two angles of another triangle, then the triangles are automatically similar. And we have that. We have that angle A is a 90-degree angle and angle O is a 90-degree angle. We also have angle Y is a 37-degree angle, and so is angle X. So we have two angles that match up, and so automatically these triangles have to be similar. That always works. If the angles match up, the triangles aren't going to hold the same ratio, and that's going to be important in a little bit. If we go through our trig, recall our trig, the word that we use when it comes to trig, the big word that we have, it's a mnemonic device, a way to remember what's what, is SOHCAHTOA. Right, SOHCAHTOA, once again, I've seen it now, we've had it in 3 videos now, is basically 3 different ratios. We have the sine ratio, which is the opposite side over the hypotenuse. We have the cosine ratio, which is the adjacent side over the hypotenuse. And we have the tangent ratio, which is the opposite side over the adjacent side. We looked at example in the last video, and with this one, what I want to focus in on, and what we're going to build to, is I want to look at 2 specific angles. I'm going to look at the sine of angle Y, and I'm also going to look at the sine of angle X. Now, those are from 2 different triangles, and so it may seem like, oh, those are 2 totally different problems. We'll see. So let's focus first on the sine of angle Y. SOHCAHTOA, sine is the opposite side over the hypotenuse. So when looking at the triangle where angle Y comes from, that's triangle day. If we look at that triangle, the opposite side of angle Y, you have to focus on angle Y, the opposite side of angle Y is 6. And then the hypotenuse, that's not going to change. No matter what angle we're looking at, the hypotenuse of that triangle day is 10 automatically. We can reduce that. We should always reduce that. Put on the big boy, big girl pants. 6 and 10 are both divisible by 2. And so we should divide them both by 2. And then there's a reason why we're going to do it. And you're going to see that reason here in just a minute. When you divide that by 2, we get 3/5. Next thing that I want to look at is as I mentioned, the sine of angle X. So switching over to the other triangle. For that triangle, the sine ratio isn't going to change. It's still going to be the opposite side compared to the hypotenuse. But in that triangle, the numbers are different. If we look at angle x, the side opposite angle x measures 21, and the hypotenuse measures 35. So when we look at that fraction, we go, okay, it's just a totally different number, nothing special. But again, we should reduce. If we look at 21 and 35, those are both divisible by 7. And so it's important that we reduce it here, because when we divide by 7, take a look at what we get. 21 divided by 7 is 3, and 35 divided by 7 is 5, and OMG, the sine of angle x and the sine of angle y are exactly the same. That is not a coincidence. If we picked another angle, say instead of angle y, say we picked angle D and looked at the sine of angle D, which would be the opposite side divided by the hypotenuse. Well, opposite of angle D, the side measures 8. The hypotenuse still measures 10. Putting on our big boy, big girl pants and reducing that puts us down to 4/5. If I take the matching angle of the other triangles, angle B matches angle D. They're in the same position. If we look at the sine of angle B, the opposite side is 28. The hypotenuse is 35. Divide those both by 7, and OMG, they're the same. They're both 4/5. That's not coincidence. Triangles that are similar have the same sine ratio, the same cosine ratio, the same tangent ratio for matching angles. If you pick angle D and look at the sine or the cosine or the tangent, the sine, the cosine, and the tangent is exactly the same for angle B as it is for angle D. Same thing for X and Y. We don't deal with A and O. A and O are 90-degree angles. We talked about that in the last video. The 90-degree angles we don't pay attention to. This is a very, very huge, important topic. This leads us to something that is the basis of Trig. It's something that will help you out in future math classes, integrated 3, pre-calculus, calculus. You need to understand that Trig, when it comes to triangles, these ratios are preserved, which means that I could have a triangle in triangle day. Let's say we get units on those, and let's say that's measured in inches. So triangle day is just a small triangle that would fit right there, 6 inches, 8 inches, 10 inches. Let's say triangle box is on a map, and it's on the world, and instead of 21 inches, 28 inches, and 35 inches, let's say that triangle box is 21 miles, 28 miles, and 35 miles. Well, it doesn't matter. Their ratios, their sines and their cosines, still work out to be the same as long as the angles match. If the angles don't match, this is not true. We have to have similar triangles, and the only way we have similar triangles, angle similarity, is if the angles match. So as long as the angles are the same, which they are, 37, 37, 90, 90, then the ratios are the same regardless of how big or how small these triangles are. That's going to make a very, very big difference as we transition to our special triangles that we already looked at in previous videos, the 45, 45, 90, and the 30, 60, 90. So we're going to need a new slide to take a look at those, so let's move to that. All right, so like magic, moving over to the next slide, I have triangle who, or how, or oh, I don't know, you go either way. So I have this triangle. I'm going to go triangle who. It's a 45, 45, 90 triangle. If you have not watched the videos on 45, 45, 90, I don't know why you're watching these out of order. There's a reason why I number them. Make sure you're watching them in order. We went through 45, 45, 90 triangles, and there's something special about a 45, 45, 90 triangle. First, a 45, 45, 90 triangle is isosceles. Isosceles means two of the sides are the same. We know two of the sides are the same because these two angles are the same. If two angles are the same, two sides are the same. That works for triangles. If you recall, I'm just going to quickly do this. If this is something that is still foreign to you, go back and watch the 45, 45, 90 video. If we say that this side is 5, I'm going to erase this, but let's just put a 5 here for now. This side would also have to be 5 because all 45, 45, 90 triangles have two sides that match. The hypotenuse, if you recall, we did the Pythagorean theorem and worked it through, and we ended up figuring out that the hypotenuse was always going to be whatever one of the sides was times the square root of 2. That always works out that way. And so if I had two sides that were 5 and 5, the hypotenuse would be 5 times the square root of 2. What I'm going to do instead of having a 5 there is I'm going to use the side length of x. That way it could be any number, right? 5, 12, 119. If this side over here is x, HO, then WH would also have to be x. It's isosceles. And by the things that we learned in previous videos in a 45, 45, 90, we know that the hypotenuse is going to be whatever the side is, x times the square root of 2. Okay? This is important. This is every 45, 45, 90 triangle that exists anywhere on any flat surface. If you draw a 45, 45, 90 triangle and make sure that the angles are exactly 45 degrees, the two sides, the two legs will be exactly the same measurement, and the hypotenuse will be the square root of 2 times one of the legs. I don't care if that triangle is 2 inches, and then the hypotenuse is 2 square root of 2 inches, or if I'm walking around the city and I do 10 miles for WH and 10 miles for HO, then I guarantee connecting W to O would be 10 times the square root of 2, and that's how long that side would be, whatever that multiplication works out to be. That's guaranteed for every triangle of this nature. That's important that you understand that fact. And so what I'm going to do is we're going to look at the trig ratios now. And so we're going to look at the sign. And notice here, instead of putting one of the letters, I'm just going to put the sign of 45 degrees. Remember, we have to put an angle here after side, a sign. I mentioned that in the very first sign video. Go back a couple of videos and you will see that. We have to have an angle there. Now, normally, all of the things that we've looked at before, the angle was a letter name. But here, instead of putting the letter name, I want to put actually 45 degrees, because it doesn't matter whether I'm talking about angle O, or if I'm talking about angle W, or if I'm talking about some other angle of some other 45 degree measurement somewhere else. It makes no difference, because remember, these triangles all share the same similarity, and so they're all in the ratio of x, and x square root of 2. So regardless of what triangle I pick, whether the sides are 5 or 12 or 100, this sign is going to work out no matter what. And so I can pick either 45 degree angle. I'll pick angle O. Okay, so let's focus on that one, but I'm going to keep the 45 there. So when I do this, remember, sine is the opposite side divided by the hypotenuse. So the opposite of that 45 degree angle measures x, and the hypotenuse measures x times the square root of 2. This is true regardless of what x is. If x is 5 or 12 or 100, this ratio is going to be whatever the side is divided by the side times the square root of 2. Always. Well, what can happen here? Those x's can reduce. I got an x in the numerator and an x in the denominator, and so if we reduce those x's, as we should always reduce our fractions, we end up with 1 over the square root of 2. Now, a rule in math that's a dated rule. We talked about this. Some teachers believe in this rule. I don't. It's old school. There's really no purpose here in 2020 to do this, but we're going to do it because it is still math. And so we'll go ahead and do it this way. And there's a purpose for it. There's a reason why. I'm going to rationalize the denominator. We don't want a square root in the denominator, so I'm going to multiply by the square root of 2 over the square root of 2. We did this back in August. This red fraction that I just created there, that's actually equal to 1, so I'm not changing the value, right? When we multiply the numerator, 1 times the square root of 2, that's just the square root of 2. In the denominator, the square root of 2 times the square root of 2 is the square root of 4. We often just say it's 4. It's not. It's the square root of 4. And what's the square root of 4? It's 2. It turns out that the sine of every single 45 degree angle is always, always, always the square root of 2 over 2. Why? Because every 45 degree angle can be made into a triangle where the opposite side is x, and then the hypotenuse will be x radical 2. We know that from previous videos, and so when we do the sine is always going to be radical 2 over 2, regardless of how big x is. Same thing's going to happen with cosine. If I do the cosine of 45 degrees, that's going to be the adjacent side, which also happens to be x over x square root of 2 if I choose, say, angle O. And so that reduces down to the exact same thing, 1 over the square root of 2. And when you rationalize that, you just get the square root of 2 over 2. Every single 45 degree angle has a sine and a cosine that are both the square root of 2 over 2. Finally, if we do the tangent of a 45 degree angle, the tangent of a 45 degree angle is going to be the opposite side divided by the adjacent side. Well, it doesn't matter which 45 degree angle I pick, be it O or be it W, the opposite side is x, the adjacent side also x, and x divided by x is going to be 1 regardless of what x is. And so we have these ratios that we can learn, that we can actually memorize, because these ratios are always going to be true for a 45 degree angle. In the next videos, we're going to look at 30, 60, 90, and we're going to actually apply these and see how they work. But for now, go back over this and make sure that you understand why these values are what they are.